Hello, I Anand Jain welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12 senior secondary physics playlist, we'll learn about magnetic force lines or the concept of magnetic flux. We will relate flux with flux density or magnetic induction and briefly understand what is permeability of magnetic media, and then we'll study Oersted Experiment and learn magnetic effect of electric current. We'll also study how Maxwell right-hand rule is used to find out the direction of magnetic field for current carrying straight conductor. So let's start. This iron ore Fe3O4 found near Turkey in Magnesia and named as magnetite, and its property like attraction of small iron pieces and line up along geometric north-south direction when freely suspended are known as magnetic properties. To explain magnetic field on the surface of Earth, Gilbert suggested that Earth itself acts like a huge size bar magnet of reasonable strength. In fact, due to molten charged metallic fluid which exists in Earth core and spin of Earth around its axis produce magnetic south polarity at geometric north pole position, and at geometric south pole position we have a magnetic north pole, and due to that there exists a magnetic field on the surface from south to north direction, and in that magnetic field a test bar magnet will align itself. When a bar magnet is freely suspended about its vertical axis, it will line up along north-south direction, and the magnet end which is in geometric north position is known as north pole, and the geometric south position pole is known as magnetic south pole. In laboratories, a tiny compass needle suspended on vertical axis and free to rotate in horizontal plane is used to find out presence of magnetic field at any position, and its one black or red colored arrow indicates north pole direction of existing magnetic field. Magnetic force line is an imaginary concept given by Michael Faraday. In reality, these force lines physically won't exist, but they produce a pictorial and visual representation of magnetic field interactions. By definition, magnetic force lines is direction of force on unit north pole. The fact is, isolated magnetic pole won't exist, but in theoretical concept, if we place only a north pole in this test position, then the direction of force on that north pole indicates the direction of force lines. In fact, these force lines indicate that path along which a compass needle aligns itself, and in any magnetic field presentation, these force lines coming out of north pole entering in south pole form a closed continuous path within magnet from south to north pole. So these magnetic force lines are always in closed continuous curves. We can say that for a bar magnet, external magnetic field force lines are from north pole to south pole everywhere, and inside the magnet they are directed from south pole to north pole. The fact is that magnetic north and south pole always exist in pair, so these magnetic force lines always form a closed continuous curve, whereas in contradiction to this, electric force lines never form closed loops, as opposite electric polarity charges positive and negative never coexist. So this is a marked difference between electric force lines and magnetic force lines. Magnetic force lines form a closed loop and electric force lines are never closed. Now this pictorial representation of electric force lines represent the magnetic field, and tangent drawn on force lines anywhere represent the direction of magnetic field as shown by these shine arrows at different positions, and the density of force lines represent the strength of magnetic field. As near bar magnetic force lines are dense, so magnetic field is stronger, and as we move away the density of force lines decreases. It indicates that strength of magnetic field decreases as we move away from bar magnet. This particular property of electric as well as magnetic force lines is very important from our examination point of view. It says that two lines of magnetic force, though they are not parallel, but they never intersect each other as it is shown here. So such intersection of force lines is not permissible, and the reason for this is that tangent drawn on force lines represent direction of magnetic field, and at point of intersection the two tangent shows two direction of magnetic field, and that is not possible. So two magnetic force lines never intersect each other. Though magnetic force lines are imaginary concept and there is no real physical existence of such force lines in space, but to express magnetic field in quantitative manner, we count these magnetic force lines, and counting of magnetic force lines is known as magnetic flux, and magnetic flux is measured in MKS unit in terms of Weber, and in CGS unit the unit of magnetic flux is called as Maxwell, and 1 MKS unit 1 Weber is equal to 10⁸ CGS unit of flux, that is Maxwell. So 1 Weber is equal to 10⁸ Maxwell. Magnetic flux density or magnetic induction, denoted by capital B, is most important physical quantity used in magnetic field studies, and by definition, amount of magnetic flux passing per unit normal area is a measure of magnetic field strength, and this measure is called as magnetic flux density, denoted by capital B. So magnetic flux density or magnetic induction is flux per unit normal area. Flux is denoted by letter phi and area is capital A, and unit of flux is in MKS unit Weber, and area is measured in meter square. So flux density or magnetic induction unit is Weber per meter square in MKS unit, and this in short form is also known as Tesla, and 1 Tesla is numerical equal to 1 Weber per meter square, and both are MKS unit, but Tesla is SI unit of magnetic induction. In CGS system, flux is measured in Maxwell, area is measured in centimeter square, and Maxwell per centimeter square is abbreviated as Gauss, and 1 Tesla is equal to 10⁴ Gauss. Now in this diagram, this complete area A is normal to these magnetic force lines, and the total amount of flux passing through it is phi. Then phi by A is magnetic induction in Weber per meter square or Tesla. If this normal area to magnetic force lines is tilted by an angle theta and got this black diagram orientation, then flux passing through the same area get reduced to this highlighted section in place of the entire amount of flux earlier passing through the same area. Since the distribution of magnetic force lines is the same whether you place this area normal to force lines or with an theta inclination to magnetic force lines, as in this second case by black diagram, the definition of flux density says that it is flux per unit normal area, and in second case when area surface got some inclination from vertical direction and this angle is theta, then its vertical normal cross section area of A area is A cos theta, and flux per unit normal area when calculated, we will find that normal area and the amount of flux both get reduced by the same proportional manner, and the ratio of flux to normal area in first case and flux which is reduced and the normal area which is again reduced got the same ratio. The ratio of flux and normal area magnetic induction remains the same, and B will not change with the change of orientation as illustrated here. In a magnetic field of induction capital B, the total amount of flux passing through any normal area is given as product of magnetic induction and normal area, and we can define this product as dot product of B vector and area vector, and we know the dot product of two vector is magnitude of first vector, magnitude of second vector, and cosine of angle between B vector and area vector. And for any area, the area vector is directed normal to the plane and is outward as shown by this n cape unit vector. N means normal here. And if area vector get tilted from its normal position by theta angle, then angle of B vector and area vector become theta, and the dot product of B and area vector will give us the amount of flux passing through any area. This numerical example will explain the theoretical concept. We have to find out the total amount of flux through an area which is 2I plus 3j meter square, where I and j are respectively unit vector along x direction and y direction, and this area is placed in a magnetic induction of 2I plus 5k Tesla, where I is unit vector along x direction and k is unit vector along z direction. And we know that flux passing through any area is dot product of B vector and area vector, and in dot product we place B vector in unit vector notation and area vector in unit vector notation, and when dot product is done, this dot product of 2I and 2I become 4I dot I, 5k and 2I will become 10k dot I, and similarly it become 2 3s are 6 I dot j, and this become 5 3s are 15 k dot j. Now the angle between I vector and I vector is 0 and cos 0 is 1. So this dot product is unity, whereas for other unit vectors, angle between two vector is 90 degree and cos 90 is 0. So these three terms become 0 and our total flux become 4 Weber. And since dot product is a scalar quantity, so flux is a scalar quantity, it won't have any direction. Magnetic permeability or relative permeability, denoted by mu and mu r, are very important to study behavior of different material in magnetic field, and this concept of permeability relate two important magnetic field quantity. One is magnetic induction, denoted by capital B and measured in Tesla, and other one is magnetic field intensity, denoted by capital H and measured in ampere per meter unit. By definition, the intensity of magnetic field is defined as force per unit magnetic pole strength. So if we place 1 Weber pole strength in a magnetic field, then the amount of force on that magnetic pole is known as intensity of magnetic field. In fact, magnetic field intensity doesn't depend upon medium, whereas magnetic induction or magnetic flux density is a medium dependent measurement, and its magnitude of magnetic induction depends upon medium permeability. And we say magnetic induction and magnetic field intensity are proportional to each other, and the proportionality constant is known as permeability of magnetic medium. Now the permeability of air or vacuum is known as mu naught, and its value is 4 pi into 10 raised to the minus 7 Henry per meter or Weber per ampere meter. This absolute magnetic permeability of air or vacuum is a constant universally, whereas permeability of any other magnetic medium is defined as mu equal to permeability of vacuum multiplied by relative permeability, and this relative permeability represent ratio of permeability with respect to permeability of vacuum, and relative permeability is a dimensionless number, whereas both permeability of medium and permeability of air are measured in Henry per meter unit. In the same magnetic field intensity, if medium is air or any other medium, then the amount of magnetic induction or flux density or flux passing per unit normal area become different, and the difference is caused by relative permeability of other media or absolute permeability of that media. Mu is different from permeability of air or vacuum. In fact, permeability of any magnetic media represent magnetic conductivity of medium, and it represent how easily magnetic force lines or flux can pass through that media. The absolute permeability of any media is defined as product of permeability of air multiplied by relative permeability, or we say relative permeability of any magnetic media is ratio of absolute permeability of media to permeability of vacuum. Now for certain magnetic material like iron, nickel, cobalt, both permeability and relative permeability are high, so the density of force lines become much more in these magnetic material in comparison to air, as illustrated in this diagram. Initially, it was believed that electric current and magnetic field has no relation, but Oersted in the year 1819 first discovered that electric current or moving charge can produce magnetic effect around it, and for a straight line motion of charge or electric current, the magnetic field is in the form of concentric circles, and the direction of magnetic field is obtained by Maxwell right-hand rule or Maxwell corkscrew rule. And Oersted discovered that the strength of magnetic field decreases as we move away from current carrying conductor, and this strength of magnetic field is directly proportional to amount of current which is producing this magnetic field. We know that a charge, whether stationary or moving, produce radial electric field, and for positive charge it is radial outward. But a stationary charge won't produce magnetic field around it, it produces only electric field, whereas a moving charge will produce both radial electric field around a charge and magnetic field in the form of concentric circle. Now if this velocity is not constant but charge moves with variable velocity with acceleration or deceleration, in that case this magnetic field become both space and time varying, and in that case space and time varying magnetic field can produce electric field, and both electric field and magnetic field together produce and sustain each other, and that become a source of energy radiation, and accelerated or deaccelerated charge can produce electromagnetic waves. Whereas in a current carrying conductor, a conductor is charge wise neutral, so such current carrying conductor won't produce electric field around them, but motion of charge produce magnetic field around current carrying conductor in the form of concentric circle. So we can summarize: a stationary charge produce only electric field, no magnetic field. A current carrying conductor produce only magnetic field, no electric field. Where a moving charge produce both electric field and magnetic field, and if charge motion is accelerated or deaccelerated, it become a source of energy radiation field or electromagnetic waves. So Oersted has discovered that a straight current carrying conductor produce around it magnetic field in the form of concentric circles, and the direction of this magnetic field, whether these concentric circles are clockwise or anti-clockwise, is given by right hand rule of Maxwell. And according to Maxwell right hand rule, if a conductor is gripped in a right hand with thumb pointing the direction of current, then the curl or the tilting direction of fingers of right hand represent the direction of magnetic field around this conductor, as in this direction current is upward, and when thumb is pointing upward direction in the direction of current, then this curl of finger in anti-clockwise direction represent concentric circle direction of magnetic field produced by this straight current. The direction of magnetic field produced by straight conductor is also obtained by Maxwell right-hand corkscrew rule, and according to right-hand corkscrew rule, if a screw is driven inside a cork in the direction of current, then the curl or rotation of right hand screw represent the direction of magnetic field around that conductor. Here in this case, we have to drive this screw in the direction of current inward to the screen, then we have to rotate this right hand screw in the direction of clockwise rotation. So for this current perpendicular to screen and inside, the magnetic field is as shown here in clockwise circles. Now these two rules of Maxwell, right hand thumb rule and right hand corkscrew rule, to find out direction of concentric circle magnetic field from straight current carrying conductor are quite identical, but definitely this right hand thumb rule is more convenient in approach. We have to find out magnetic field around a north director conductor current. So let's assume that north is top upward direction and south is just opposite to it, and east and west can also be obtained from this directional diagram. And when current is directed along north, then as per right hand thumb rule, when thumb is pointing in the direction of current, then the curl of right hand around this conductor in anti-clockwise direction represent the direction of concentric circle magnetic field. So this magnetic field at top of conductor is from west to east direction, and to bottom of this current the magnetic field is directed from east to west, and to this north directed current to eastern side the magnetic field is vertically downward, and to west side the magnetic field is vertically upward. If a negative charge is coming out normal to this paper plane in upward direction, then we have to find out direction of magnetic field around this moving charge. So we know current is directed in the direction of positive charge movement, and for negative charge movement in this direction, current is directed in opposite direction as shown by a red arrow. And if we use right hand thumb rule and thumb of right hand is pointed in the direction of current, then this curl of right hand finger indicate the direction of magnetic field around this conductor in clockwise direction. And for this conductor, if this shan arrow shows the north side of this moving charge, then to north of this moving charge the magnetic field is directed in east direction, and for this moving charge to south of it magnetic field is westward, and to east of this moving charge the magnetic field is towards south direction, and to west side of it magnetic field is towards north. We hope this introductory informative video of magnetic field has explained the concept of magnetic force lines, magnetic flux, flux density, magnetic permeability, and it also explained you Oersted discovery and magnetic effect of electric current. And now you also know how the direction of magnetic field from a straight current carrying conductor is obtained by Maxwell rule. Our other learning video of this playlist of senior secondary physics are equally useful in our exam success. And if you need our online doubt clearing classes, do join our YouTube channel membership by clicking join button just beneath. Thank you very much.